Okay, Newton's second law is easily argued to be one of the most important principles in physics, and we write it as F net equals ma, like that. Okay, so something external to your system causes it to accelerate. Some applied force, a net force, causes it to accelerate inversely proportional to the mass. All right, now we're going to introduce a new way of looking at this. This is not any new physics, but it ends up being very powerful. In some regards, more powerful than this direct look at Newton's second law. So to do so, I'm going to focus on this side right now. I'm going to say, okay, ma, well, what is A? A is dv dt. Okay, it's the derivative of velocity with respect to time. Well, mass in most situations is a constant, okay? And in what we've dealt with, we've held it as a constant. So a derivative with respect to a constant doesn't do anything. So I can bring that mass in to that derivative of time. So do the time derivative of mass times velocity. And it means it's no different. It doesn't mean anything different. Okay, so I can pull this out and in or out as much as I'd like. Well, this quantity right here, we give a name. We call that momentum. And we give it a variable p. It's a vector because velocity is a vector. So it's a scaled velocity in a sense, but it's proportional to the mass in addition to the velocity. And so the phrase momentum. And our question is, well, what does this do? What is this momentum? All right, so let me just ask a couple questions. What if we had a model rocket, some small model rocket, and it's flying, and model rockets can fly pretty darn fast when you ignite their engines. Let's say it's flying 500 meters per second. That'd be pretty darn fast, but we'll just say it is flying 500 meters per second. That's supersonic, so that's a pretty fast one. But let's go and say we got this really fast, crazy fast rocket, but it's pretty small. I'm going to say it's 1 kilogram. All right. I guess for a rocket that's not teeny small, but in order to get 500 meters per second, that would have to be a pretty big rocket. Okay. And so what is its momentum? Well, P equals mv in magnitude, and so that's going to be 1 kilogram times 500 meters per second, and so I get 500 kilogram meters per second. Okay, and I'm going to turn off my phone because it keeps dinging here. So the units of momentum are kilogram meters per second. All right, and this has 500. So just kind of give you a perspective. A really fast, this is a supersonic rocket that weighs about a kilogram, a couple pounds, has a momentum of 500 kilogram meters per second. Well, what about a football player? We have a pretty beefy football player. Forgive my inability to draw the beef. So here's a big football player. Let's just say that this football player is running along down the sidelines of the field at 5 meters per second. You know, so that's not the fastest football player I've seen, but a decent clip running down the field. And let's say that this is a moderate-sized football player at 100 kilograms, 220 pounds. All right, what's this person's momentum? Well, P equals mv. We get 100 kilograms times 5 meters per second. Excuse me. And that's going to equal 500 kilograms meters per second. So this small, very fast thing has the same momentum as this large, very slow thing, or slowish thing. And so momentum seems to be, okay, well, what's so great about that? What's pretty interesting about this is, we'll see in a later video, is that momentum is conserved in nearly every case. It's such a powerful conservation law that the usefulness of thinking of Newton's second law in terms of momentum are very broad, very applicable, and we can solve some very complex problems with conservation of momentum. So it's important to define momentum clearly and understand how it's related to force. Okay, so let's step on to that force side now. So we've understood this momentum. Well, what's this force side thing? So I'm going to rewrite it. I got F net equals dP dt. Okay, and just like all other cases, F net's a vector, which makes P a vector. So I have to be careful with components in this case. All right. So if I focus on just one component, let's say F net x equals dpx dt. Just focus on that right now. Okay. P is mass times velocity. Often the mass is the same, so it's kind of just a scaled velocity. But I can measure that. I can measure that a lot. And so often I can see how some objects change its speed, and I can measure that. And I can figure out, oh, well, what's the force then acting on it? But sometimes things happen so fast, like a collision or an explosion happens so fast, it's really hard to figure out how big that was because the time was so small. Okay? So sometimes we take this time and we multiply it up. Remember, this is a derivative, but in physics, derivatives are just really small changes. So that's just a really small number there, and I can multiply it up. And I end up with dpx equals f net x dt. Okay. Now, if the force is constant over that time period, I can just say delta px equals f net x delta t. And this quantity here is, in the case of a collision, pretty difficult to calculate. Or the force is pretty difficult to calculate. The time might be a little bit easier to calculate, but this is easy to calculate. I can see how fast it's moving before the collision, and I can see how fast it's moving after the collision. And so I can find the change in momentum. Therefore, I can find this combined quantity, and we call this impulse and give it a variable j. We call it impulse. And it is a vector, and so in this case, since I've been working on the x components, that's jx, or the impulse in the x direction. Okay. So sometimes I don't really need to know the details of how the force was happening. I just need to know the total effect because it's going to be visible in the change in momentum. Now, if it's not constant, so I couldn't turn these small changes into a big change, well, that's all right. I can say delta px is just an integral of f net x dt from an initial time to some final time. And then I'd integrate over that. But what is an integral? An integral is just an area under the curve. Okay? And so if I have an f net versus time, so here's f net x, and it looks something like that, some really hard, complicated changing thing, well, I could still find the change in momentum by just adding up all the area under this curve, with curves below the time axis being negative. So this is a new way of looking at it. We now have delta p vector equals j vector. Our change in momentum is equal to the impulse.